Hello. Yeah. Before starting today's session, let me make a small announcement. So in the evening, after the second talk, let's say around 5:40, we will have an informal discussion session with today's speakers and last week's speakers. So let me start by introducing Professor Sergei Gukov from Caltech, and he will tell us about S-duality in geometric Langlands.
Well, thank you very much for introduction, and more importantly, thank you to all of the organizers, especially to Aswin for his very hard work to invite me here, and I'm excited to learn many new things during this week. So I have to start by sort of apologizing right away that, and I'm making it clear that today I'll focus on some physics introduction to geometric Langlands, or physics approach, or introduction to physics approach to geometric Langlands. And this will be different subject from other lectures that I'm going to give later. So other lectures, different subjects. And also very different style. Today, this is supposed to be a survey. So my job is not to explain anything, really. And just to connect as many things as possible. And here, the goal will actually be to explain things, so it will be much more pedagogical. So the reason I mention it now is that if you feel completely lost or uninterested in today's lecture, it may not mean the same for tomorrow, and vice versa. So, before I get to physics interpretation of geometric Langlands, which roughly will be the second half of the talk, I thought it makes sense to motivate why geometric Langlands is interesting in the first place. And it's not so much for specific form of the conjectures, which I'll state at some point, but rather for connections that it makes between different subjects, which include number theory. So that's one subject that goes into Langlands program. In fact, non-geometric Langlands program, that's classical. Then there is geometry, even different type of geometry that goes into geometric version of the program, and representation theory. So the usual Langlands correspondence of number theorists takes different parts from these different subjects and blends them together in a rather surprising, interesting way. So the reason people are interested is precisely for this network of connections. I'm not going to be able to explain many of them, but I'll try to give you a hint of how each one of these arrows looks like. So I'll give you examples from several of these connections, and as you may notice, physics is not part of it. So then, but two of the items from the title of this program are, so namely, it's called quantum fields, geometry and representation theory, and geometry and representation theory are on the board, so physics will come later, or quantum field theory will come later. So first, I'll try to focus, let's say, on perhaps this connection between number theory and geometry, and this will be topic number one. So there are many subjects in number theory where geometry, or you could say emergent geometry, comes out of the blue as a surprise, and one of them has to do with the theory of modular forms. So modular forms are functions which enjoy nice transformations with respect to SL to Z or various subgroups of SL to Z or various other analogous groups. So it means that if you have some function of tau, f of tau, then f of a tau plus b divided by a tau plus d, c tau plus d, is up to some prefactor, is the same as f of tau. And in number theory, you get various interesting subfields of this area depending on what exactly you require here as a transformation. The most classical example is that appears in most of the textbooks is where you have c tau plus d to the power k, and this power k is called the weight of the modular form. And in particular, it means if, so notice that A and B do not appear here on the right-hand side, which means that you're allowed to shift tau by any integer, which means that such a function, f of tau, actually can be written as a power series in variable q, so sum over n, say from 1 to infinity, an q to the n, where q is exponential of 2 pi I tau. So writing it as such with integer values of n will essentially guarantee that such a function is invariant under T transformation, which shifts tau by +1. But of course, then you have to ask, when does it also enjoy transformation with respect to S element of SL2Z or corresponding subgroup? So that's a non-trivial question. It's interesting to study spaces of such modular forms of different weights. And again, it's a very typical subject in number theory. And first, I choose one, and for experts, that means I'm focusing on cusp forms. But I'll suppress, again, this is survey, so I'll suppress the differences between bundles and sheaves, cusp forms, and such. So therefore, I'll try to speak fluently, sometimes really meaning what I say, but suppressing the reason why. Yeah. So the statement I'm aiming for is better phrased with for cusp forms. Right, so, and again, we'll approach many of these topics from so I'll try to emphasize the most essential points and ask most kind of essential questions, focusing on big picture. So here, the big picture is in part that the way these modular forms are defined, and that's why I decided to review for you a definition, makes it completely non-obvious that some of these coefficients, an, have to be integers. So that, of course, comes out quite often, not always, by the way, but quite often. And as both of our morning speakers already emphasized earlier today, if you see some integers in the expansion of a function, you have to ask yourself what these integers are counting. So where are they coming from when they're counting? So to answer this question in this setup, it's convenient to take function and transform it a little bit. So there is a so-called Mellin transform. Now this is part of a much more general story, which this is a name usually used in number theory textbooks. In textbooks on complex analysis or on analysis, you see exactly the same transform under a different name. It's called Borel transform. And this connection or this interpretation actually makes nice contact with yet another subject, which is so-called resurgent analysis. That's not the only connection, but I mention it now because there will be a couple of other places where analogous phenomena will appear. And what is the Mellin transform? So if you have a function f, like ours, then Mellin transform of that function is basically the integral from 0 to infinity of f of x, x to the power s, dx over x, this sort of integral. So you can introduce logarithmic variable, write log of x, and rewrite it as exponential of s times that variable. There are several different ways. But you can try to apply this sort of transform to modular form to learn something interesting about it. And what you learn is that the resulting function usually has nice, interesting analytic properties on a complex plane as a function of complex valued argument S. And this gives you the L series. But to be a little bit more precise, I'll be interested in so-called Dirichlet L series attached to our function f of tau, thinking that I'm mostly interested in modular forms. And by definition, you can also make the following definition that L function of our f as a function of s is basically sum over n, say from 1 to infinity, of an over n to the power s. Okay? So this is essentially this closely related cousin of the Mellin transform. There are usually two versions of L functions. One is usually called lambda, that has nicer properties if you're interested in behavior on complex plane. The other is L, which is closer to interpretation of integrality of the coefficients, where I'm aiming at. And then it turns out that if you repackage information about your original modular form of weight k, what happens is that this can be written as a product, and this is yet another connection to other lectures that you'll see over and over again. In fact, both of our morning speakers kind of used it, that sometimes if you have a function, it's convenient, and it's complicated enough, it's convenient to rewrite the sum, which is how it's given to you, in the form of the product. And again, though both speakers this morning didn't really emphasize that, that was what was going on. So this sum, which looks somewhat complicated, constructed out of the original input, can be written as a product. And the product is over primes p of the form 1 divided by 1 minus ap, p to the power minus s, plus p to the k minus 1 minus 2s. Okay. And now you can ask, does it bring us any closer to interpretation of this coefficients AP? And the answer is yes, that for k equals 2, so when the weight is equal to 2, then 1 plus p minus the APs which appear here in denominators are precisely the numbers of points on elliptic curve defined over FP. So here is an example, rather famous example, where geometry appears in a number theory problem kind of out of the blue. And what I just reviewed, so let's see. Is a statement of famous Taniyama-Well conjectures. Yes, I believe so. Yeah, so here I'm suppressing primes of bed reduction and all of that. So I'm assuming that, right, so there is an interesting story. What happens if your equation for elliptic curve and P have something in common, namely that some kind of prime of reduction occurs, but if that doesn't happen, so that kind of degenerate phenomenon, then basically what this says is that all ANs can be expressed in terms of APs. And that's actually how this first appeared in the works of Hecke, and that gave rise to the Hecke theory. So that's actually what this formula is saying, that there is a way to repackage information about ANs just in terms of APs for P prime. And that's, again, the generic phenomenon that this is trying to convey us. So a theorem which used to be Taniyama-Wei conjecture Say it again. Yes. Well, this is almost like this is essentially the zeta function. Or right, so that's why it's not identical to zeta function. It's L function, but it's a close cousin. So indeed, it's so yeah, this is closely related to theory of zeta functions and wave conjectures, which usually tell you how to factor the denominator, but that's a bit different. So that's not identical. So don't try to expect that this should be really equal. Yeah. Okay, so what's the statement of the conjecture is that for every elliptic curve E over Q, there exists a cusp form, so that's a precise statement, but again, I don't want to focus on all such details. I want to convey the flavor, because if I focus too much on details, I'll never get anywhere, of weight 2 for some congruent subgroup of SL to Z, gamma 0 of n, such that L function for this cusp form, for this modular form, is the same as L function of elliptic curve, essentially defined by the right-hand side of that equation. So it basically says that this phenomenon should happen, and there is a nice match between such modular forms and geometry, or rather algebraic geometry over finite fields for elliptic curves. So this is example of a connection between number theory and geometry, where geometry pops out of the blue, and this leads to interesting connection. You can naturally ask how to generalize this to higher weight k. So here I presented for you a little bit of the story for general k, and only in the end specialized to case of weight 2. And if you ask this question, it actually is the subject of active research. So this sometimes goes by the name of modularity conjectures and requires a lot more technology. The basic idea is that this weight is correlated with the dimension of algebraic variety. So elliptic curves appear only because we're in the smallest interesting weight. And if you ask for higher weights, you'll be dealing with algebraic geometry over fields in varieties of high dimension. So let me give you another example of such connection between other topics involved here. And what I'm aiming at is give you a flavor of what kind of subjects appear, how they connect to possibly other talks, and so that then we can see later physics incarnation of some of these phenomena and their analogs. So all of this Langlands correspondence is really about analogies of various types. So number 2 is going to be, let's say, between representation theory and geometry. Where the statement would be that geometry of various varieties, or some geometric objects on various varieties, have to do with representations, if varieties have something to do with the group. So suppose, for example, that G, as will be in the rest of my talk, compact Lie group. If you're not a representation theorist, think of SU2, that's good enough. In fact, that's going to be rich enough story to continue the discussion. And then the usual Borel-Bott theorem said that finite dimensional representations of G can be identified with spaces of sections of line bundle or more general bundles on G mod various subgroups, G mod H. And this kind of statement is a baby version of a more general program, which usually goes by the name of orbit method, and more generally sometimes referred as one of the main problems in geometric representation theory, that says roughly the following, that if you have, so geometry of orbit or conjugacy class of G, of the group G, knows that there is a connection between representations of G. So in fact, here, it's not necessarily, if it's compact, it basically boils down to a theorem, so namely this Borel-Well-Bott theorem. But if G is non-compact, and later on I'll use the following notations, that GC will be the complexification of G, and G sub R will be some real form of GC. Then, in those cases, there is no all-encompassing theorem, but there is an all-encompassing theory developed by David Vaughan and many others that connects the geometry of some orbits or conjugacy classes, or more precisely, geometry of various bundles on those conjugacy classes, and representations of G. So, I'll give you an example in a second. I'll go to the other part of the board, but just to list one more item here of the same flavor, these are all pretty much same statements in increasing degree of complexity, starting with the simplest, which is the statement of Borel-Well-Bott theorem, then this more general study. If you try to make it a little bit more precise, and I'll mention the reason why you need that, you introduce here a more and more sophisticated object. So here I try to phrase it in terms of something fairly familiar, but then very quickly it leads you to a notion of so-called sheets, which are finite unions of orbits or conjugacy classes, and also leads to statements such as what's known as geometric Satake correspondence, which is rather an evolved version of such statement that says, if you're interested in representations of the group G, then they have something to do with, I'll say, bundles. But this is, of course, not quite correct. Again, I'm using oversimplification from my earlier disclaimer on what's called affine Grossmanian, of which you can think as a usual Grossmanian. We are all familiar with usual Grossmanian, which is basically space of, say, k-dimensional planes in n-dimensional vector space. But if you try to make analogous notion over function fields, you naturally run to notion of affine Grossmanian. So one of the general themes in geometric representation theory is to connect representations of some group G, be it real, compact, or complex, to typically bundles on some spaces. So that's a very general thing. Now, I'll give you an example of which fits in some sense to most of what appeared on the blackboard. What is an orbit or a conjugacy class? It basically means that you can pick an element x, either in Lie algebra or from the group G, and start acting on it with the group G by usual adjoint or co-adjoint action. So this gives you an orbit, or in the group theory case, an exponentiated version, a conjugacy class. And simple example is, again, if, say, G is SU2, you can pick any element in SU2 and try to run this procedure. Say, if you pick identity element, if X happens to be identity, then it doesn't matter how you conjugate it, you're going to produce the same element. So that's an example where this conjugacy class or orbit will be just a point, because action will keep the identity. But if you pick generic element of SU2, what will happen is that you can reach any other element of SU2 by adjoint action, as long as elements of the group that you're using do not commute with a given element X. And for generic X, there is usually just U1 subgroup of SU2 which commutes with it. So you quickly learn that in this case, O is simply going to be homogeneous space, SU2 mod U1, which is precisely the same thing as CP1. And as a result, you can realize your familiar representations of SU2, finite dimensional representations of SU2, as sections of various bundles on CP1. So that's a typical statement that you get in this way. So in particular, you can get representations such as trivial, adjoint of SU2, and so on and so forth, the familiar sequence of representation. Now, why do we need more sophisticated technology? Again, I don't have a lot of time to explain it, but there is an interesting phenomenon that happens here, that suppose you have some representation V of SU2, and you know that a three-dimensional representation sits here inside. Okay? Then, in the case of finite dimensional representations of compact groups G, what happens is that there is no other choice for it to be a direct summand in V. But in general, if we move away from finite dimensional representations of compact groups, that's not the case. So what may happen is that you have, for example, a representation, say, 2 plus 3, or its analog, and it sits inside V in such a way that this exact sequence does not split. So 2 and 3 and whatever else appears here are not necessarily direct summands. Okay? So this is quite interesting phenomenon, and it leads you to, naturally leads you to notion of extensions of representations, and requires a little bit more sophisticated technology to describe, because now you can ask, well, if you told me that representation can be realized as some sort of geometric object, how do I form an extension? What does it mean? How does geometry reflect that? And phenomena, partial answers to, or maybe complete answers to this question, you'll see in talks of Satoshi Nawata and possibly Duque, who will discuss analogous phenomena happening in geometry of Hitchin moduli space, which will appear a little later in our discussion. And it should be interpreted as bound state formation of branes or EPS objects, which, so physicists probably can relate to this line. Mathematicians can certainly be more happy with extensions of representations, but they're actually similar phenomena if you use this context of geometric representation theory. Okay, any questions? So these are different examples. So top row here, so there are roughly, what I'm mentioning is 3 types of statements an increasing degree of complexity. One is a classical theorem, and it's well-defined. It has very specific set of assumptions. The other is more of a program, again, which goes under this word orbit method, and which says the following, that if you form such a conjugacy class or orbit, it always happens to be a nice phase space symplectic manifold that you can quantize, so thinking about it as phase space in classical mechanics, sorry, in quantum mechanics, and then you obtain the corresponding representation as a result of quantization. So basically that's the philosophy here. So then there are two actually different but related notions, or I'm just throwing keywords, which are trying to make this program more systematic so that it could be raised as a theorem, as a general statement with specified assumptions. In one form, it requires you introducing this notion of sheets by Borrow, which combines several conjugacy classes together sometimes. So what I just said is a little bit oversimplified for a general theorem. And the other is a somewhat geometric statement of geometric Sateki correspondence, is also an upgrade, but in a slightly different direction, that involves, which is kind of builds in these extensions in place right away, and has to do with categorical structure, namely there is a tensor product on representations and morphisms that it takes into account. Okay. So again, this is just a glimpse of what connection between, in this case, geometry and representation theory typically looks like. And it's somewhat surprising that there is such a nice marriage between two different subjects. Okay, any other questions? Okay, so now I proceed to number 3. And for number 3, I have nothing left but to talk about this relation. Which is relation between number theory and representation theory. And here actually I'll just state the, one of the statements of conjectures, one of the conjectures in the Langlands program. But I want to emphasize the difference between the classical case and geometric case. So, yeah? Geometry appearing in, a priori, they're very different. That's a really good question. So I just took 2 random examples, which I try to cover as much territory as you can see and make as many connections as I can. So unfortunately, this geometry is not the same, but we could have tried to relate geometry of those varieties, which I just erased, to number theory. That would still work. I mean, there would be still a nice story, but that's just a poor choice of example. Okay. Right, so in the statement of some of the Langlands conjectures, there are several different versions which work at different levels. So first of all, you can consider finite fields and make a set of statements. So then you can consider number fields, such as, say, q extended by square root of -2. That's an example. So then you can go to function fields, where things start becoming infinite dimensional, and finally reach geometric Langlands and physics as the top of this program. And again, there are different levels. The reason I mentioned this is that even the statement I'm going to phrase next can be formulated in each of these categories. And this direction brings us closer to physics, but this opposite direction, if you go up, is what's usually called classical. So this is just to help with the terminology, classical version of Langlands conjectures, when you try to go away from function fields or anything infinite dimensional, work ideally with either finite fields or number fields, kind of like we saw in our questions a moment ago. So, and in each of these frameworks, so I'm going to make a statement which can be equally phrased in all of these different versions. First, rather far from the bottom, and that's precisely the statement of one of the Langlands conjectures, which says that n-dimensional representations, which I'm going to call sigma, of the Galois group of the closure of F over F correspond to irreducible automorphic representations which I'm going to call pi of GLN. And over what field you define, both sides is again, depends on where exactly you want to work with, but this is kind of, for the survey, is a type of question that usually is taken as formulation. So again, I'm not going to explain all these words, but I'll explain some bits and pieces. For example, instead of telling you the precise definition of automorphic representation, it suffices to say that it can be realized in a nice class of functions on a homogeneous space, kind of like those functions of bundles that we saw earlier. Yeah, this is obviously number theory side. This is more representation theory side, if you wish, and that's the statement of the correspondence. Now, by itself, it wouldn't be as interesting if it didn't come with rich additional structure, and in particular, so sigma maps to pi, that's what I want to record, and in particular what happens is that on this set of automorphic representations of GLN, you have a nice action of algebra which is very large and interesting, and it's called spherical Hecke algebra. So in this setting, spherical Hecke algebra is nothing but the algebra of symmetric polynomials. So this is a statement of so-called Satake isomorphism, which says that in case of GLM, this is nothing but C of Z1 plus minus 1, and so on, up to Zn plus minus n, symmetrized with respect to Sn. And there is a corresponding, so you should think of it as particular algebra that acts on these objects, and in good situation, which is called corresponds to unramified choice of such a reducible representation pi, it can be nicely matched to certain data on the left-hand side. So again, without deep explanation, I want to say that there are certain parameters or invariants that you're supposed to match across this correspondence. So on this side, these are called eigenvalues. So set of certain parameters, I'll call them Z1 of pi, and so on, Zn of pi, are supposed to nicely match to analogous parameters Z1 of sigma up to Zn of sigma, which are defined completely differently on the left-hand side, and these are called Hecke eigenvalues. And these are called Frobenius eigenvalues. Of course, I realize that I'm not giving you full definitions, but the reason I mention this is because, first of all, I want to say that there are certain things that are supposed to match, and actually their physical counterparts I can explain. This is a little bit outside of my domain. But another reason I mention this is that this is attached to name of Ramanujan, and I thought that this would be a crime if I give a lecture and miss the opportunity to mention it in the context of geometric Langlands correspondence. And it also gives me an opportunity to illustrate this dictionary between practical versus closer to physics or geometric version. Why? Because a theorem, which, just like in case of Taniyama-Well conjectures, used to be a conjecture, and in fact it's a conjecture of Ramanujan Peterson, but now it's a theorem which says that absolute value of the zi's of pi is equal to 1 for unramified or good choice of this automorphic representation pi. So again, I mentioned this before, I didn't explain it, just said that it's something nice, but that's one of the statements which carries the name of Ramanujan. But it's actually, so this I'm not going to explain, but I'm going to explain its classical version. Of this conjecture, which actually is very concrete and recognizable, just like everything in usual standard number theory, that, so this is called just Ramanujan conjecture. And it's proved by Deligne. And it's a statement about essentially discriminant function. So if you take q and product over m from 1 to infinity of 1 minus q to the m to the 24th power, and again use the same trick or same principle where it's often useful idea or good idea to convert sum into a product and product into a sum. So you can write this as a sum over n from 1 to infinity, coefficients tau of n, q to the n. Then this conjecture states that tau of p, absolute value, is less than or equal to 2 times p to the 11 halves, and sometimes it's called 11 halves conjecture, for prime p. Okay. So this is something very concrete. Again, now it's a theorem due to Deligne, and even though it does not look immediately exactly like this, it's supposed to be a classical version of that statement. So now I want to come to this statement of Langlands conjecture and rewrite it, gradually transform it in a language that eventually brings us to physics. So the first thing to do is to try to formulate it not for GLN, but for more general groups. That's one of the first places where Langlands correspondence or Langlands notion of Langlands dual group appears. And are there any questions before I move on to the second part? So I'm essentially done with brief overview of phenomena that connect number theory, geometry, and representation theory. And in the rest of the talk, my goal is to take this phenomena and show you the geometric, or if you wish, physical counterpart. I don't know, but isn't it not the 24th power, just this product itself? Yeah, so you'll be counting like partitions over. Yeah, I don't know. That's a good question. Yeah, honestly, I don't know. Some of this also connects to combinatorics, which I guess could be yet another corner, and. Okay, so I'm going to take this statement and overlay it with a couple of equivalent versions or slightly different versions. But the reason I state it without deep explanation, some of the classical story is so I can make analogies and tell you what elements of the classical story, what becomes of them in a geometric or perhaps even in a physical context. So with a broad brush, this side is called Galois side. This side is called automorphic side, hopefully for reasons which are somewhat obvious, even though I didn't explain those details. And what the conjecture tries to do is to associate some representation pi to representation sigma in such a way that certain invariants match with respect to spherical Hecke algebra action. So all of the statements which I just recapped have their analog in the geometric world. And that's what we're going to discuss. So first thing, as I already alluded to, is to try to take just this classical statement of Langlands conjectures and phrase it for group G. And this is already quite interesting, where if I try to phrase it not for Cartan type A for GLN, but for more general G, things become quite rich. So the corresponding statement would be that here, Galois representation of some group G, or corresponds to something analogous to what we have seen before, even though without deeper pursuit. We saw that in the case of representation, sometimes conjugacy classes combine into packets called sheets of Borrow and Joseph, Tony Joseph. And here, there is analogous notion of L packets of automorphic representations for a different group. So previously it was n-dimensional versus GLN, and now what's going to happen is that analogous statement involves different groups. So usually they are denoted G and G check, G and LG, and I'm going to put Langlands dual on this side, since this is convention used in most of the physics literature. And this brings an obvious question: what are G and LG? And the answer is the following. So you can make a table that for group G, there is a corresponding dual called Langlands dual group. And if I'm, again, treating G compact group, not the reductive group as it's usually used in mathematical literature, but rather compactly group G, which was my original notation, then the case of GLN should be really called UN. And in this case, the dual group is the same. That's why we didn't need the notion in the previous version, in the previous discussion. But if you consider already something more interesting, such as SUN, or in mathematics literature, you would see this as SLN case, then the corresponding dual group will be PSUN, which is the same as SUN divided by its center Zn. And this is actually the general property of this duality between group G and its Langlands dual. Yeah. Well, this was Galois representation, so you can think of it as representation from Galois group, Galois f bar over f into GLN. So that's basically to say that we have an n-dimensional representation. So that could be, in some sense, another way to phrase it. And that statement will have an obvious analog in a second. Now, right, so this is part of the general dictionary that for a D type, so G and LG have same Cartan type if they're of Cartan type ADE. So for instance, here we're talking about Cartan type A, and that doesn't really change. But what changes is that the center, which I'll denote by Z, of one group becomes the fundamental group of Langlands dual. And here you see, for instance, that SUN is simply connected, but has non-trivial center Zn. And this conversely, because it's a quotient of something connected, simply connected by Zn, it has fundamental group, but no longer the center. So they exchange their role, and that's a general feature. So for example, I can write the case of D, SO2n. This is Cartan type Dn. And Langlands dual is also the same, SO2n. And the same is going to be true for exceptional groups, such as E8, for instance, it's self-dual. But then once you go to Cartan types B and C, things again become a little bit more interesting. So for example, SPn is dual to SO2n plus 1. That's Cartan type B, that's Cartan type C, outside of simply laced. And for instance, if you take just maybe one more, G2 is going to be same as G2. So this is the notion of Langlands dual group, and it already appears in a classical program, but then that's going to be important for physics interpretation. And now I want to kind of start switching gears even further, that we already saw several spaces appearing in the context of geometric representation theory. These are usually spaces which have nice sort of either G symmetry or where G acts. And in particular, we saw various examples of, say, coadjoint orbits or conjugacy classes. And these conjugacy classes are spaces of solutions to some partial differential equations on Riemann surfaces. So this is the space, this is the place where Riemann surfaces appear. We already have a lot of group theoretic data, but now I want to introduce real geometry in the sense of geometric Langlands of Riemann surfaces, which I'm going to denote by C. So C stands for a curve. And first observation or statement is that if you write Kitchen's equations, which is a set of partial differential equations for G bundles and actions of canonical bundle on the Riemann surface, the Higgs field, which have the following form. Curvature of the connection is moment map for some Higgs field phi, then dA of phi is 0, and likewise dA of star phi is 0. And denote the moduli space of solutions to these equations by M sub h of type G and C. So it depends on choice of group theoretic data, group G, and the Riemann surface C. Then, what we saw before, so remark, is our orbits / conjugacy classes that we already saw are examples of such moduli spaces where the Riemann surface is basically punctured disk. So it's a disk with a puncture. Yeah, specific prescription of boundary conditions or type of the puncture. And therefore, it suggests natural generalization to move away from punctured disk, which is actually the statement of local geometric Langlands, to more general Riemann surfaces and consider same statements as before, but now thinking about such replacement where you replace, say, orbit or conjugacy class by entire Hitchin moduli space for, say, closed Riemann surface C. So that's one way to, if you wish, enter the geometric Langlands and its physical interpretation. Another way is the following, that the global presentations that we had here are analogs for if you ask what is the analog of the Gola group for Riemann surface, and it also has a natural counterpart, namely in moving away from this classical case, Galois group has to be replaced, or if you wish, corresponds to fundamental group of a Riemann surface C. Okay? And if likewise you ask, so previously we were asking, what is the space of representations from Galois group to some group G, or its complex version? So analogous question here will be, what is the space of representations of pi1 of C, because now this is the analog of the Galois group into something, say, Langlands dual of GC, then this again turns, well, by definition, this is nothing but the space of complex flat connections on a Riemann surface, but it's well known that this is isomorphic in one of its complex structures to precisely that same space of solutions to Hitchin equation for group G, or rather LG if I'm using it here, on a Riemann surface C. So that's yet another way to go from classical story to geometric Langlands. And now, if you do that, you can make yet another modification of the statement, now in the context of geometric Langlands. So I'll say that this is now geometric version. That irreducible G local systems, or if you wish, points on this variety, on this space of complex flat connections, LG, in fact, systems on C correspond to Hecke eigensheaves on Bun-G. Okay. So this is the statement of geometric Langlands, and Hecke eigensheaves is an analogous statement to what we had here, and this irreducible G local, LG local system is analog of the Galois representation. As you see, it sounds horribly complicated, but roughly speaking, what it means is that points on this space here map into something which behaves nicely with respect to behavior, with respect to analog of the spherical Hecke algebra, which also exists in the geometric setup. And now this brings me to my last point, namely how all of this should be embedded in physics. We already got very close by talking about some gauge theory on a Riemann surface and PDEs. And basically, if you want to translate, so I've been making a slow path from classical Langlands to geometric Langlands and now to physics. If you want to study physics approach to geometric Langlands, you can work at two different levels. So you have a choice, and both are okay, both are good possibilities. So one level, to understand what this, for physicists, very complicated looking statement can possibly mean, is to work with sigma model. So there are two levels to understand this statement. So one is sigma model. A target space, which is Hitchin moduli space, or space of solutions to the Hitchin equation on the Riemann surface C here, and its counterpart for the Langlands dual group. So that's one level. And the second option, which is closely related, is to work in four-dimensional, so-called n equals 4 superring mills. Which is formulated for gauge group LG on one side and leaves on some four-dimensional space, which involves product of your Riemann surface C with something else. So let's say R2 for simplicity. And here it will be G, and it leaves on same space, C cross R2. And the reason that such interpretation is even possible is that if you ask where in physics or math, say, this Langlands dual group appears, there are essentially three places. And we have seen all three of them in this talk. So one place is in Langlands correspondence, even in classical version, but of course also in geometric version. Another is in relation between moduli spaces of solutions to Hitchin's equations, where this phenomenon is known as a famous mirror symmetry, or example of famous mirror symmetry, and could have, and in fact it was, discovered somewhat independently of any gauge theory or any other interpretation or application to Langlands, where each of these spaces are non-compact local Calabi-Yaus, and you can ask, as Calabi-Yaus, can I see the mirror of, say, this Calabi-Yau? And what turns out is that the mirror is precisely the same type of space, but for the dual group. So that's basically the key point of the sigma model approach, which rests on work of Tamas Hausel and Tadeusz. And in the context of gauge theory, this is the third place where Langlands dual groups appear, namely this interesting theory, 4D n equals 4 superring mills, has non-trivial duality called S-duality, which relates a theory on any four manifold with a gauge group G to another theory on the same four manifold with a Langlands dual group. And basically, these three places, namely Langlands correspondence, mirror symmetry for Hitchin moduli spaces, and n equals 4 superring mills, are the only three places, at least that I know, where Langlands dual groups naturally appear. So if you know yet another application or yet another aspect or branch of physics or math where Langlands dual groups naturally come up, let me know. I think that would be interesting to connect it, but these are pretty much all the spaces, or all the places I know. Now, natural question then is, how do we connect these three subjects, namely sigma model, superring mills, And our initial starting point, which will be item number 3 now, the geometric Langlands correspondence. So these two are related by essentially compactification on Riemann surface C. So if you're a physicist, you know what I'm talking about. If you're not a physicist, whatever I'm going to say will not shed much light. But this is a fairly standard operation of compactification or dimensional reduction on a Riemann surface C. And it's actually a fun exercise, which was done by Bershadsky, Johansson, Saurav, and Waffa, and then in a slightly different form by Harvey, Moore, and Strominger, to try to solve equations of motion, or rather BPS equations in n equals 4 super-Young Mills, and try to perform this Kaluza-Klein reduction and see what kind of sigma model you get as a result. And of course, they find that from n equals 4 super-Young Mills, you get precisely the sigma model in the Hitchin moduli space. And moreover, they were the ones who actually, from physics point of view, proposed that S-duality becomes T-duality or mirror symmetry in the sigma model context. So these two are related by a fairly clear operation. So then let's see how we can rephrase this geometric Langlands in the language, say, of a sigma model, and there will be analogous formulation in terms of gauge theory. Any questions? Okay, so this is the last point, and we're already very, very close. In fact, I kind of gave you a hint of what's going to happen. So these G-local systems on C are basically point-like objects in or points on this Hitchin moduli space. So what we're trying to ask is what happens to a point under mirror symmetry? That's the question we're really asking. So let's see what, yeah. Yes. Not entirely. So the way we're going to reformulate it still will be quite asymmetric. So in fact, right, S-duality as symmetry is symmetric, but then question is, what do we ask? What exact question we ask? And the exact questions that we ask will actually be quite asymmetric. Maybe I'll try to summarize it now. That was my plan, and you'll see for yourself that it's not exactly the same. So yeah, I'm debating what to erase. I guess I'll erase this part. So there are a couple of observations we can make to make a physics counterpart of that statement of Langlands conjecture that's still on the board. So first of all, every point in Hitchin moduli space MH for Langlands dual group, I just decided to name Galois side with LG. So I hope it's not a problem since G has to come in somewhere. So point I want to point out is object which is fairly nice. In fact, it's holomorphic in all complex structures of Hitchin moduli space, and it carries infinitely many. So it's a pretty cool thing. It's triholomorphic. This terminology has to do with the fact that usually this infinite set of complex structures is expressed in terms of standard basis of phi, j, and k, and then that's what tri refers to. And this can be also phrased by saying that it's a certain object, namely brane, of type BBB. Okay? Because B branes in the story that involves mirror symmetry, and that you probably heard a lot more about from Rondonaghi are B-branes are holomorphic in the corresponding complex structure. So for the natural setting for this right-hand side, so the left-hand side of the correspondence is the set of these BBB branes on MH for Langlands dual group. So let's take this as an approximation for our correspondence and ask what's going to be on the right-hand side. Here we have to think a little bit because, see, physical setup indeed is somewhat symmetric. That's what you're pointing out, and involves Hitchin moduli space on both sides. But here we actually don't even see Hitchin moduli space or anything similar. So just like here, we have to do some interpretation. So it has to do with the fact that Ban-G, which we don't have to know what it is half-dimensional space, in fact, the most interesting part, in some sense, of Hitchin space. And you can say that M Hitchin space for group G on the Riemann surface C is, roughly speaking, but this is huge roughly, so that's a big lie. And I hope that Satoshi will tell us a lot more, and you'll see actually very explicitly how much it is a lie. Cotangent bundle to Ban-G, total space of the cotangent bundle to Ban-G. So therefore, we already have some connection, but in order to really bridge the gap between Ban-G, or rather T star Ban-G, and Hitchin moduli space, we have to say that such Hecke eigensheaves, or more precisely D-modules in this setting, actually can be realized as A-branes on the dual space. And therefore, the corresponding statement will be that here we're looking for branes of type, let's see, BAA, branes on MH for the group G on the Riemann surface C. Okay? Yeah, so the first one in the notations of Hitchin is actually fixed because in this complex structure, this mirror symmetry is a Fourier-Mukai transform. It's actually a holomorphic operation. But it's on a T-duality, and which in the sense of mirror symmetry relates A-branes and B-branes and other complex structures. So that's actually what we expect here, because this, whatever these Hecke eigensheaves are, they're supposed to be more like A-branes, or rather, the support of a D-module is basically the A-brane. So it is asymmetric already here, that you should think of this side, which was originally Galois, as B-model side, whereas this automorphic side is supposed to be A model. And as you can guess, A model is usually more complicated than B model, and same is true in number theory context. Automorphic side is more complicated than Galois side, well, roughly speaking, usually. In addition, it wouldn't be good enough if we didn't have this action of Hecke algebra. So remember that algebra of symmetric functions, symmetric polynomials. So it's a commutative algebra, and in physics, it's realized as algebra of Wilson lines, algebra of Wilson operators. Oh, sorry, 't Hooft operators. I'm jumping ahead of myself. And that were not sigma model, but rather gauge theory comes handy because it immediately says that under this S-duality, 't Hooft operators map into Wilson operators, and in fact, it's a fun exercise to verify that this point like BBB branes are in fact eigenbranes with respect to action of this algebra of Wilson operators. And the two sets map into each other with respect to S-duality or this mirror symmetry. So to summarize, and sorry for, well, actually I'm pretty much on time. To summarize what this physics interpretation of geometric Langlands does, it basically is a package that relates different types of branes, A branes versus B branes, on Hitchin moduli spaces for the group G and Langlands dual group, and this map is consistent with an action of Hecke algebras of various types. Here, we encountered so-called spherical Hecke algebra, which I mentioned before, and again, that was a commutative algebra. The reason it is commutative is because from the physics point of view, this may be helpful to physicists, if you try to take OPE of line operators in four-dimensional space, it doesn't matter whether you approach line 1 and line 2 in this order or this order. You can move them around. You have a lot of space around to move them. So that's why corresponding Hecke algebra is spherical, which means commutative, but the moment you have something which favors a plane on which these line operators are stuck, and in the physics context, this additional data usually comes in the form of surface operator, that will lead to generalization of this algebra and generalization of this story, which will have non-commutative Hecke algebra, namely various forms of affine Hecke algebra. So the last thing I want to make, the last remark, is that ramification, which means that on a Riemann surface C, you have now particular points where something bad happens, and in number theory case, ramification is unavoidable, so you have to consider such case in general. This is realized in physics corresponds to surface operators, which in our story are supported points on this Riemann surface and span the other two dimensions, which I called R2 before. So you have this kind of two-dimensional support of a surface operator. And now if you try to ask for two line operators, say line 1 and line 2, to form OPE, namely take a product in one order and compare it to the opposite order, they don't necessarily have to agree. And what this OPE tells you is actually giving you various versions of non-spherical Hecke algebra, such as affine and various other deformations. And I promise you that you'll recognize some of the words and topics that were mentioned in various other talks. For example, Dupay will tell you a lot about map of A branes and B branes under this geometric Langlands duality. So basically, he'll zoom in on one particular aspect, and in the lecture of Satoshi, you'll see what spherical really means and why M. Hitchin is not quite the same as T star of Bungie. Right. Thank you for your attention.
So is there an intrinsic A-model interpretation of this Hecke algebra? In terms of the Fukaya category or something?
Yes, there is. So in both A model and B model, you can think of Hecke algebras as, or these corresponding operators as functors acting on Fukaya category and derived category. So the rough version of this question would be, what are the autoequivalences of, say, Fukaya category here and derived category here? That's not quite the question we really want to ask, because we care about this particular branes. So it's not the autoequivalence of the entire category, but rather this special class of branes. So that's the type of question that you would consider on either A side and B side. And you can realize some of them, some of these functors, as correspondences, especially on A side.
So in your original discussion, you had the orbit method for various groups. In particular, you have a version of all this story for other types of groups when the base field is not algebraically closed. And so we have the geometric Langlands, the geometric Satake for real groups. We understand fairly well how the geometry for those works. Is there a version of the supersymmetric gauge theory that would make sense for non-compact real forms? Is some orientifolding process that you can perform that would correspond exactly, say, to the geometric Satake for real groups or the Langlands for real?
So there are actually two questions that you packaged in one. Yes. So one is, how does do the highlights of geometric representation theory embed into the story? And I wouldn't mention them in the beginning if they didn't. So they do, and that's a beautiful, rich story. So you can embed relation to representations of, say, group G, not meaning now compact, just any, in fact, even real group. Geometric Satake correspondence, and in both cases, this additional gadgets or animals that live in the zoo of four-dimensional theory, such as surface operators and other defects, come in. So I didn't really have much time to explain it, but they're still there. And you mentioned also the second, one more remark I want to make on your question related to orientifold. So that's really, in some sense, yet another subject which one could have talked about. How, so here I focused on two-dimensional story of a sigma model and four-dimensional story of a gauge theory, but you could ask, how is it realized in string theory? Because you can realize this n equals 4 superring meals on the world volume of D3 branes. And then natural question, so that would lead only to Cartan type A by default. So you can ask, what do I do to get other Cartan types? And how do I relate SL to Z duality of n equals 4 superring meals to analogous duality of type 2B string theory? So that would indeed involve orientifolds and actually will be highly non-trivial. So for a long time, I thought that they just trivially coincide. For example, type 2B coupling constantly becomes coupling constant on D3 branes or something like that, and they transform in a similar way. But actually, that's not true. And unfortunately, this is not in the literature. I want to advertise that for non-simply laced types, which you mentioned involving orientifolds, that's actually somewhat very subtle story. I was thinking of whether I should mention it or not in the talk. I'll be happy to discuss it privately. But that's surprisingly, so embedding this in 10-dimensional type 2B is yet another subject which currently in the literature, even in the most referenced papers, is not quite well described and not quite correct. Well, that's true, and that's why I always thought that I understood it, that embedding is very trivial, but it's actually surprisingly is not. So over the past year, we had intense discussion with Yuji Tachikawa, and in fact, some of the questions that I emailed you occasionally are related to that discussion. So that's why we were interested in orientifolds, and this embedding is highly non-trivial. So therefore, I want to separate two parts of your question. To one part, the answer is that it has been studied and it's somewhat documented in the literature, but the other part, surprisingly, is something I didn't touch at all, and actually there is a lot to say for non-simply laced groups. So embedding in type 2B is highly non-trivial. On the A model side. So basically this conditions which are something like irreducible usually means that your brain has one component. So that's typically what it means. So on the A model side, it will mean that it's not direct sum, but some of these notions become blurry because you quickly pass from individual objects to, or from individual branes or submanifolds to objects in a derived category. So you actually have to consider not just, say, disjoint union of two Lagrangians, but actually derived version of the Fukaya category and therefore complexes and so on. So that's, again, I didn't want to mention categories that much, but usually, so this notion of irreducibility becomes either blurry or replaced by something else in a categorical world. That's more precise. Yes, yeah. Yeah, so in this case, well, anyway, yeah. In fact, if I were to discuss it more fully, I would probably have to go into stacks, and that's territory that's best described in work of Danagi and Pantev. And that would be, actually, that's more useful, also related to answering question about non-simply laced cases. So that's something I want to advertise. Well, I wouldn't say it's entirely classical because if it was really classical, you know, the whole, even at the level of sigma model, the whole mirror symmetry program would be simple and classical, but it's not really. So it is somewhat classical if you think about it in complex structure I, where it's Fourier Mukai transform, but even that now is applied to varieties with lots of singular fibers, and you have to, yeah, it's not entirely classical. Yes. No. That's precisely what we touched just a moment ago. So in fact, if you start asking, again, it depends. I think that the honest answer is depends on how deep you look. If you ask for, say, generic point here, a skyscraper shape, this BBB brane, at a very generic point, things are relatively nice. And you can limit yourself to that and declare victory. But then people, of course, want something interesting or peculiar. So they tend to send these points into singular points on the Hitchin moduli space where there are singular fibers. And again, I'm sure you'll hear more about this, if not from Satoshi and then from Dupay. And then question becomes, what do we do with the singular points? So geometry of target becomes singular, so something has to come to the rescue. So and gauge theory comes to the rescue. So that's where zooming on those questions and trying to answer them will require, on the mathematical side, language of stacks or something else that can answer it. And physics behind it is really the gauge theory. Gauge coupling enters questions which are usually referred as quantum geometric Langlands and trying to make both sides indeed more on equal footing. So in that case, what happens is that it's not just B side and A side as cleanly as I described it today. Both are kind of deformed so that completely different kind of form opens up related to kind of non-commutative deformation of branes on the one hand, and again, in the math literature, this is quantum geometric Langlands, and the gauge coupling, or more precisely, the parameter that Kapustin-Witten called psi, enters the story in a crucial way. But yeah, that's another aspect. No, it's yeah. But don't underestimate. I mean, this side and Hooft operators is highly non-trivial. I mean, this A-branes and Hooft operators. That's not classical. It's if you really want to answer it in full glory, that's as quantum as it gets.